Hi, in this video we would design a simple project using VHDL and then we will test that and integrate that into the FPGA board. The project we are doing today is very common and you must see them in your day-to-day appliances such as electricity meter, which can display voltage and ampere and wattage in the same screen but one by one. Or you might see them in a stabilizer where input voltage and output voltage display on the same screen but one by one. Or you might see them on the microwaves where time and temperature displays on the same screen but at different time. So there are many real life use cases of this project. So today we will design a simple version of a similar requirement. We would be talking about that in some time. So coming back to today's scope, we will talk about components and items which we'll be using in today's project. Next, we will brief that how you will operate 7-segment display for your project today. Next, we will design our entity for our VHDL module. Then we will brief the architecture for today's design. Next, we will review the simulation results from waveforms. Then we will review the RTL schematic of our project. And finally, we will integrate our system into the FPGA board and we will see our live design. So let's start today's session. Okay, this is the system which we are designing today. I believe most of you must seen similar things and you can already relate this with real life uses. This is similar to digital meter which is displaying voltage and current on the 7-segment display, and there is an indicator LED, green for ampere and red for voltage. So at one time voltage displays on the screen and after some time ampere displays, and this is happening in the loop at fixed time gap. So we will be designing its simpler version, so we will only display first digit of this reading, not the decimal data. This means for current digit 2 will display and for voltage digit 4 will display. So let's see how we will design this. Before we start, let's quickly go through some basics of 7-segment display which are easily available in the market. We already had the detailed explanation on 7-segment displays in last video, and we designed our BCD to 7-segment decoder too. So we are not going in deep in this video, but if you are new to 7-segment display and its functioning, then you should definitely check out that video. I will paste the link in the description. So in this basic 7-segment display, there are 7 LEDs which are packed inside a package in this structure, and the structure is able to illuminate 0 to 9 digits by switching some LEDs on and some LEDs off. So we only need to control which LED should on and which LED should off to illuminate any specific digit on this display. For example, if we wish to display 0 on this, we will switch on all the LEDs but switch off this middle one that is named as Z. Similarly, for digit 1, we will switch on LED B and LED C. Let's see digit 8. For this, all the LEDs are on. Look for digit 6 and digit 9. For digit 6, this LED will not glow. Other all LEDs will on. Same for digit 9. This LED will not glow, but all other LEDs should switch on. That's it. This is the basic fundamental of 7-segment displays mapping. So based on 4-bit BCD input, which is binary conversion of decimal input, we will control output to display the same digit on 7-segment. So there are 4 binary input lines to the module and 8-bit long output for 7-segment display. 1 additional pin for decimal point. Okay, so for 0 digit, the 7-segment output should be this. For digit 1, our 7-segment output will be this. Similarly for digit 2, similarly for digit 3, for digit 4, for digit 5, for digit 6, for digit 7, for digit 8, for digit 9, and all zeros for others. Simple, right? As I said, in this video we would be designing the same system but with 1-digit display output. So quick brief, first we will have 2 inputs. One is for voltage and second is for ampere, and these will display on the 7-segment display one by one. So for current or ampere, it will display 2 on the screen, and for voltage it will show 4 on the display, and that will continue all the time in a fixed time cycle, say after half a second or after a second. So for this we will need a clock input as well, which will control the selection on input that either voltage or ampere will display on this screen. And we will have one output for 7 segment display driver, which will control 7 segment displays LEDs. So this will be 8 bit in length. Easy, right? So first we will design the entity for this project. Okay, this is our module. First is library declaration. Then we will have the entity design. So type entity VA meter is port clock in std underscore logic, volt in std underscore logic underscore vector 3 down to 0. So this is 4-bit long. Same ampere in std underscore logic underscore vector 3 down to 0. So this is again 4-bit long. Next, meter out std underscore logic underscore vector 7 down to 0, because this is 8-bit output. Then bracket close, semicolon, and VA meter, semicolon. Next, we will design our architecture. So for architecture, type architecture behavior of VA meter is, then we will declare one internal signal for selection line for volt and ampere. This means it will carry either voltage or ampere at any specific point of time. So type signal S colon std underscore logic underscore vector 3 down to 0 semicolon. Note that this must be the same length as ampere and volts input. Next we will type begin, then process clock comma volt comma ampere, then begin. If clock is equals to 0, then S gets the value of volt semicolon, else S gets the value of ampere semicolon, and if and process. Now next section would be the BCD to 7 segment decoder, where S will be our input line and target line would be our module output, means 7 segment display pins. So with S select meter out gets the value of this when S is equals to 0 0 0 0, comma this when S is equals to 0 0 0 when, this when 2, this when 3, this when 4, this when 5, this when 6, this when 7, this when 8, this when 9, and this when others, and semicolon, and last line and behavior. Next we will see its simulation results and RTL schematic. So this is our simulation result. This is just a screenshot to give a quick review. Later we will simulate it properly on the tool. So at this yellow marker, we see the values of our signals at that specific point of time. So at this time, clock is 0, means volt input will move to our internal signal S, which is value 0100, means decimal 4. So 4 will move from volt input to internal signal S. Then based on this signal, which is carrying voltage, we'll drive the 7 segment display decoder, and we will see this at the output, which will glow 4 on 7 segment display. Also, this will glow the first LED indicator, which would represent that this is volt indication or voltage indication. Similarly, for another timestamp, when clock is 1, ampere will move to signal S, and then we will see digit 2 on the 7 segment display. You can take a small pause here if wanted to verify waveforms and its values. Next, we will discuss its RTL schematic. This is RTL schematic of our design. So these are our two inputs. First is ampere and second is volt. This is our third input, which is clock frequency. If you notice from our architecture in our last slide, this is a simple multiplexer design where clock input will be treated as selection signal, and based on that either voltage input or ampere input will move to the output. So for 0, volt input will be the output, and for clock value 1, ampere will be the output. So you just use multiplexer design in this practical use case. And because we have 4-bit input lines, so we see 4 multiplexer here, 1 each for 1 bit. Next, this will go to our BCD to 7 segment decoder here, and then we will get the final output. This is more detailed view of our schematic. Next, we will modify our design little for FPGA integration. Now, because we are going to integrate this design into the FPGA, but for that we will need little changes in this code. So this is our original architecture code, and we just need a small change. because in this design we are using clock input for displaying either ampere or volt on the 7-segment display. But the problem is that this clock frequency is our board frequency, and that is 50 megahertz fixed, and we cannot see anything on the display at this high frequency. So we will use a frequency divider which will cut down this high frequency to nearly half or 1 hertz cycle. So think a bit that what changes you will make on this original code for this new requirement. You can pause here to complete this task, and we will match our results in next slide. Okay, let's match our codes now. So first we created an internal signal which will act as internal clock. So its name is int underscore clock. So type here signal int underscore clock std underscore logic semicolon. Next we will create a variable inside this process, and we will set its initial value as all zeros. So type variable m std underscore logic underscore vector 25 down to 0 colon equals to others gets 0 semicolon. Next we will type these few lines which will cut down our frequency to reasonable cycle. It's just a dummy system, so we don't care of exact 1 second cycle. So we type if rising edge of clock then m colon equals to m plus 1 semicolon, and if and we moved m25 in int underscore clock. So typed int underscore clock gets a value of m25. If you know any alternate way to design frequency divider, then you can use that way too, because there are many ways to do this, but the purpose is just to cut down the frequency or the master clock frequency to nearly 1 hertz cycle, so that we can see the digits on the display one by one at 1 hertz of cycle. Now next we will use int underscore clock to drive the selection of volt and ampere input. So this is one more change. There is one more change we need in the sensitivity list, because now we are using int underscore clock inside the process. So this must include in the sensitivity list as well. So add int underscore clock in the sensitivity list. We also need to include few more libraries in the list to use +1 with std underscore logic underscore vector in this code, which are use IEEE.std underscore logic underscore earth arith.all semicolon, use IEEE.numeric underscore std.all, use IEEE.std underscore logic underscore unsigned.all semicolon. Let's move to the FPGA integration then. So first we will do the simulation, and then we will do the FPGA integration. So for simulation we are using Xilinx ISC for today's task. So we will open the project navigator. Okay, so this is opening. So first VirtualBox is opening. Okay, so this is our VirtualBox, and we will open the project navigator. Okay, so this is our project window. So we will creating a new project. So go to file, click on new project, give some name. Suppose we are giving VA underscore meter, then click on next. Because we are only doing simulation, so no matter what you are setting here, but make sure preferred language is VSGL, then next. This is summary, just review it and click on finish. Now we will create the new source, so click on this. We are writing on VSGL, so click on VSGL module and give the name VA underscore meter. Next, this is entity name and this is architecture name. You can give the port list here, but we are just copying and paste, so we are not filling it here. Click on next, summary, then finish. So this is our basic structure of our VSGL code, but we will delete this. Now we will copy our code which we have explained in the PPT, and copy, then paste on the project navigator. So okay, so you can see this is library declaration, this is entity, and this is clock input std underscore logic, voltage as an input vector, ampere std vector 3 down to 0. Now this is RG for LED indicator, that is volt or green, so 1 down to 0. Next is meter out, so this is output type vector 7 down to 0, and entity. Next is architecture, so this is architecture, signal S std logic vector 3 down to 0. Next begin. Now created a process for selection. So if clock equals to 0, then S gets a value of volt and RZ 10, else S gets a value of ampere, RZ 01. And if and process. Now this is our decoder which convert VCD to 7-segment display driver. So with S select, so now we are using signal S as an input signal for the VCD, and this is our output of the decoder in the last AND behavior. So save this. Now click on check syntax. Okay, all good. Now go to the simulation tab, just write it later. So click on simulation. Now select this. Now expand this and click on simulate behavior model. So double click. Okay, so this is the simulation window. Now first give a restart. Now these are inputs and outputs. So little tune it up and down. Now give clock. So this is a clock frequency. So we'll give a clock. So leading adds value 0, trailing adds value 1, period cycles 1 microsecond, apply. Okay. Now give voltage as 4, so force constant. So value is 0, 1, 0, 0, apply. Now give ampere some value, so right click, force constant, it is 2, so 0, 0, 1, 0, apply. Okay. Now run it for some specific time, so I'll run it for 10 microsecond and click on this button. Now zoom it little or fix it little to the window. Now move to the yellow marker to some place where we are going to check our values. So this is our values. So you can see, so this is clock 0. So this means we should see voltage in the signal. So you can see 0100 move to the signal S, which is our internal signal, and based on this 0100 we are getting the output. So this is indication of voltage and this is the output of decoder. So this decoder output will display 4 on the display on the 7-segment screen. Now the clock value is 1. So ampere will move to the internal signal. So ampere is 0010, that will move to the signal S. Now the indication will show the second LED which will says this is ampere, and we are getting the decoder output which will drive the 7-segment display. Same way you can check it for any other instances, because we are just using 2 values for ampere and voltage, it would be same. Now suppose we are changing some input, suppose we are changing amperes, so right click. Now suppose we are giving some random value 1000, apply. Okay, so this is value 8 as a numerical value. So now click on it. So you can see, so ampere 1000 and it means 8 will move to the signal S. So signal S is 1009. Now you can see the output, all are ones. So as I said, for each, all the 7-segment LEDs will on. Now jump back to the ISC project navigator. Now click on view RTL schematic. Now we are looking for the RTL structure of our design. So click on the second option. Now okay, so this is our design. So this is VA meter, ampere, volt and clock as an input, meter out and RZ as an output. And this is our module. Double click on it. So you can see the structure. So these are all multiplexer. These are inputs, volt, ampere, clock. Now this is a simple multiplexer because we have 4, then we are getting 4 multiplexer, and the last we have decoder. So double click on the multiplexer. So you can see this is a simple design of a 2-in-1 multiplexer. Same for the next. Now double click on view technology schematic. Okay, so this is little more detailed structure. So you can see it here. Next, we will modify our code little for the FPGA integration, and we will integrate that into the FPGA. So let's start. So we have the Cyclone 2 device, and for that we will use Quartus Prime. So we'll type Quartus Prime and we will open this 10.1 web edition. So we will click on create a new project. Okay. Next, so give some location. So I'm making a new folder with name VA_meter. Select it and click on OK. Now give the project name. So we are giving VA_meter. Next. Next, now we will select our device. So we have Cyclone 2 package NEQFP. So 208 pin we have. Now this is the device we have. So select this and click on next. We are not doing the simulation here, so it doesn't matter what you selected. Click on next. So finish. So first we will create a new VSGL module. So click on this and select the VSGL file. So here we will copy and paste our VSGL code. So this is our VSGL code. So copy it and paste it here in the file. So this is our library declaration. This is entity. We made a little change, so we are not giving the input volt and ampere here. I will tell you in some time why we did this. So instead input, we created two new signals for volt and ampere. So this is in the same length that we have in the input lines, and we hard coded the volt value to 0010. So this is digit 2, and we hard coded the ampere value to number 4. Other than that, everything is same like we discussed. So save this. So give some location. So we will navigate to the save folder and we will save this file. Save. Now the next step is to check the syntax error for our code. So we will compile our code. So click on compile design. So now it is compiling our code. Okay, so everything is good. Click on OK. Now the next step is to plan the pins of our FPGA with our module. So we'll click on the pin planner. So this is our FPGA device and there are 4 sides. There are a lot of pins. Now we are defining which pin will be connected to our module output or input. Now we have defined all the 7 segment output pins. Now we are setting red and green LED pin. So RG1. Okay, so we have set all the 7 segment outputs and the LED outputs, but still we didn't get the clock input. So we will set pin number 23 for this clock input. So pin 23 is set for the clock frequency. Now go back to the Quartus Prime. Now the next step is to generate the file or generate the programming file. So click on assembler. So it will generate the program file for us. Okay, so it is done. Now the next step is to open the program device, open programmer. So click on this. So this is our programming file and this is our FPGA device. So it's already detected. Now we just need to click on start and it's 100% successful. Now let's see the output on the FPGA and 7 segment display. If you found this video helpful, please give it a like and leave a comment below, and don't forget to subscribe for regular updates.